Hi students, in last class we have discussed regarding objectives and limitations of series compensation and power transfer characteristics regarding series compensation. And today we shall discuss regarding the compensation by sectioning, that is dynamic shunt compensation and concept fundamental concept. The main thing is here, if a synchronous machine is connected at an intermediate point along a long transmission line. You can see here, if a synchronous machine is connected at an intermediate point along a long transmission line, it can maintain a constant the voltage at the point, just as the terminal synchronous machines do at the end. If we use a synchronous machines, we can maintain the constant voltage here. Why we use a synchronous machine is connected either intermediate, or if we can connect intermediate, because for long transmission lines, okay, it can maintain the constant the voltage at that point, just as the terminal synchronous machines do at the end. Okay, so synchronous machines will do at the terminal synchronous machines will do at the end. It will maintain a constant voltage. If we use that only in intermediate points, then we can maintain the constant the voltage. In so doing, it divides the line into two sections which are apparently quite independent. What they are saying is dividing the line into two sections. Okay, the voltage profile, the maximum transmissible power and the reactive power requirement of each section can be determined separately. The voltage profile, maximum transmissible power and the reactive power requirement of each section can be determined separately. If we divide these sections, so we can determine the voltage profile, maximum transmissible power and reactive power requirement of each section. If we divide this line into sections, so we can easily identify the maximum transmissible power, reactive power requirement of each sections. This section 1, section 2, section 3. Okay, 1, 2, 3, like this. So the maximum transmissible power in particularly is now determined by the weakest link in the chain. So how they will determine means the maximum, how much we can transfer, how much we can transmit the power, maximum transmissible power in a particular is now determined by the weakest link in the chain. For example, we have divided into sections. Okay, the weakest link, or it may be the near to the generation, near to the load, or it in between only it will be a weakest link that can be picked out, and we can determine the maximum transmissible power. For example, if a line is sectioned into two equal halves, okay, then if shunt capacitance is neglected, for example, they have taken the line, they have divided into two sections, okay, that to equal. Okay, if we neglect the shunt capacitance, then the power transmission characteristic is given by equation, that is delta will change to delta by 2, because we have divided the line into two sections. So the delta will become delta by 2, XL will become XL by 2, with ES is equal to ER is equal to E. So the equation will become P is equal to 2 into EM into E divided by XL into sine delta by 2. So EM is here, EM is nothing but what? EM is the midpoint voltage. So that will be constant by the synchronous machines or some other constant voltage compensating device. The midpoint voltage will be constant either by using a synchronous machines or by using any compensating device. Okay, the maximum transmissible power will be doubled. You can see when we maintain the constant voltage. P is equal to what it is there, 2 into em into E. So the maximum transmissible power will be doubled here. This scheme called compensation by sectioning, this was proposed by F.G. Baum in 1921. He proposed that this scheme compensation was proposed by F.G. Baum in 1921. He suggested that connecting a synchronous condenser at intervals, for example T1, T2, T3 for 10 seconds, for 10 miles, like that. Particular distance, intervals means particular distance, for example 50 miles, for 50 miles if we connect again for 50 miles, like that, intervals. Okay. Baum suggested that by connecting synchronous condenser at intervals of 100 miles, a substantially flat voltage profile could be achieved at all levels of power transmission. He suggested that if we use a synchronous condenser for 100 miles intervals, then we can maintain a flat voltage profile at all levels of the power transmission, And Baum considered only the voltage regulation and reactive power requirement in detail. He did not consider the stability. Okay, he considered only the 2 points here, voltage regulation and reactive power. Okay, he considered only voltage regulation and reactive power. He did not consider the stability point here. It was not until much later that the stability of long lines compensated in this way was adequately understood for practical use. If losses are neglected, the compensating current taken by the intermediate synchronous machines is purely reactive, and the machine supplies or absorbs only reactive to form the to or from the line. They are saying that if losses are neglected, then the compensating devices we are using, the compensating current taken by the intermediate synchronous machines. If we neglect the losses, what happens is compensating current that will taken by the intermediate synchronous machines. We use the synchronous machines to maintain a voltage constant, that will take the compensating current, and it is synchronous machines is purely reactive. It is and so the machine will start observing. Okay, either it will start observing or it will generate the supply. Okay, that is what they are saying. If we neglect the losses, the compensating current will take by the what we connect the intermediate synchronous machines, that will it is mainly purely reactive, because the machine is synchronous machine, it is a reactive device. Okay, so the compensating current will take by the synchronous machine, either it will observe the reactive power or it will generate the reactive power from the line. In the steady state, therefore, the machine can maintain constant voltage at its point of connection without requiring a mechanical prime mover. What they are saying, in the steady state condition, the machine can maintain a constant voltage. Okay, it does not require any compensating device, or it does not need a point of connection without requiring a mechanical prime mover. The ratio has the dimensions of a susceptance, which is capacitance E if IY lead V and inductive if V leads IY. This is the compensating current. This implies that synchronous machine could in steady state be replaced by a capacitor or a reactor. And this implies that the synchronous machines should be replaced by either capacitor or reactor in the steady state condition. If the steady state condition is no need of synchronous machines, that can be replaced by a capacitor or a reactor. In order to restore to V, in order to restore V to the constant value, required to maintain the independence of the line sections, the capacitive or inductive susceptance would have to change also. If the susceptance of a real capacitor or reactor could be modulated or controlled in such a way as to maintain constant voltage at its point of connection, the device would be functionally equivalent to the synchronous machines. They are saying that the value of the susceptance of real capacitor or reactor, it may be modulated and it should be controlled in such a way. We need to, in order to maintain a constant voltage, we need to modulate, or we need to control the susceptance of real capacitor or reactor. If we use a capacitor, we need to control or modulate the susceptance of capacitor. If we use a reactor, then we need to control the susceptance of a reactor in order to maintain what? In order to maintain a constant voltage. That this is similar to synchronous machines only. So far, it has been implied that the shunt compensating device must maintain constant voltage at its point of connection. The theory of compensation by sectioning in the steady state of very slowly varying conditions, that is slowly enough for the rate of change of kinetic energy of rotating machines to be negligible. In spite of this, it is seen that in certain regimes, compensation by sectioning is an essentially dynamic process in the control engineer's sense. Okay, the compensation by sectioning is very important in the dynamic process. In next class, we shall discuss with the other topics.